Okay, so we're here to look at a few of these homework problems. There's a few little nitpicky things that happened here. The big ideas of the section involve that we know that if you take the derivative of position, then you're looking at a velocity function, and the derivative of velocity is acceleration. Well, if you go backwards from those, if you integrate acceleration, you're at velocity, and if you integrate velocity, you're at position. So if you have a velocity function and you integrate it and find the area under a certain region, that's going to be the displacement or the amount of change in position in that area. So that's the kind of thing that we're looking at here. So the object is moving in a positive direction when its velocity is positive. And then on this one, the one thing that's a little tricky, they want you to include the 0. I'm not 100% sure why. I probably would have put a parentheses there. It's a little nitpicky thing, but anyway, a bracket on the 0 on this one. And then use the values shown in the graph to set up an expression that gives the displacement of the object over the interval 0, 9. So if you're going from 0 to 9, you would basically want to integrate and find this area here, the green, and then integrate and find the area here, and then subtract them. And that would be the displacement over that time. So here, we don't have to integrate because they already have the areas for us. It'd be 13 minus 15, which is a negative 2 displacement. And then if we wanted to do the total distance traveled from 3 to 15. So now what we're talking about is not displacement. Displacement is how far it's moved from its original position. But here what we're talking about is how far it moved altogether. So you want to think about a car like driving down a road one way and then backing up. Well, it moved all of this way, but it only actually displaced the difference between the two. But on this part from 3 to 15, you would add the 15 plus 12. It went 27 miles. If we want the displacement over the whole 0 to 15, that'd be 13 minus 15 plus 12, which is 10. So it wants us to describe the position of the object relative to the initial position after 15 hours. It is to the left of its initial displacement after 15 hours, and it's negative. If it's at its initial position, then it's 0, and if it's to the right, then that quantity is positive. Select the correct choice below and fill in the box if necessary. After 15 hours, the object is 10 miles to the right of its initial position. Okay. Number 2 is kind of similar to that. Let's go ahead and look at number 3. Explain the meaning of position, displacement, and distance traveled as they apply to an object moving along a line. So the correct answer here is C, the position of an object moving along a line, which is all we're doing really in this section, is the location of the object relative to the origin. The displacement is the change in position between time t equals a and t equals b. The distance traveled between t equals a and t equals b is the integral from a to b of the absolute value of vt dt, where vt is the velocity at time t. So if you're going to find displacement, then you would integrate vt over that region. If you want to find distance traveled, that's when you integrate absolute value. It's like going back to this question, and if we wanted total distance traveled, we would add the 12, the 16, and the 10, whereas displacement, you don't integrate with absolute value. You add the values as they are. You do 12 minus 16 plus 10. So that's the difference between displacement and total distance traveled. So question 4, suppose the velocity of an object moving along a line is positive. So it's always going forward. Are the position, displacement, and distance traveled equal? Well, the answer to this one is that the displacement and the distance traveled will be equal, because that integral that you would do from a to b of vt is the same as the integral from a to b of the absolute value of vt in this case, because it's always positive. So your displacement and distance traveled would be equal. But those things may not be equal to your position because you don't know where you started. Maybe you didn't start at the origin, maybe you're already 50 miles down the road. So the position may not be the same as that distance traveled and displacement, although those are both the same. So this has got a little bit different terminology. It's just a little more general question, but we can think about it in terms of position, although it could work for other things as well. Basically, if you have position and its initial value, and then you also have the rate of change. So in a position thing, this would be like velocity, right? And we want to find the position at a future time. Well, what we're going to do is integrate from where we started to where we end of that velocity. And we know that's going to give us our displacement, so how far we are from our initial position. And then if you add that to your initial position, that will give you your new position. So let's say, I started 12 miles down the road, and then I had this velocity, and I traveled this velocity function, and I traveled along that for 2 hours. That would tell me, I ended up 8 more miles down the road. That would give me 12 plus 8 is 20. Now, the only thing this is saying is that this works for things other than velocity and position. This could also be like profits, right? I have my initial profits, what they were on March the 1st. I have some kind of function that defined the change in my profits over time. I integrate that between 0 and the next year, and then I could see how where my profits ended up after that. It could also be something about temperatures and temperature changes, so work for almost any quantity. Okay, the last type of problem that you're going to see on here really goes to tie in acceleration, velocity, and position. For this problem, we have an acceleration function, then we have an initial velocity and an initial position, which we'll need all of those things to be able to actually solve to get the original position function without having a bunch of variables in there. We'll talk about that as we go. But it's very important that you have those initial conditions to be able to solve this fully. So our acceleration function is pretty simple one. It's negative 0.07 t. So we know if we integrate acceleration, that will get us to our velocity function. So negative 0.07 t squared over 2, which is negative 0.035 t squared, but plus c. Do not forget that. Now, in this case, we can actually figure out what the c is by using our initial velocity that they gave us. We know that v, when evaluated at 0, gives us 13. Well, if this is v, and you evaluate that when t is 0, that's just going to leave c to be 13. So actually our v of t is negative 0.035 t squared plus 13. Well, now to get to our s of t, our position, we're going to integrate again, negative 0.035 t cubed over 3, which turns out to be this number, negative 0.0117, plus 13t plus c again, or maybe you want to be a little more careful because these are not the same. You could call these c1 and c2. It really doesn't make any difference on this problem. But in this case, the initial position is 0, which means that s when t is 0 is 0. So if you put 0 in for t here, both of these go to 0. And you're just left with c2 equals to 0. So c2 just goes away. And what you're left with is negative 0.0117 t cubed plus 13t. Now, if you didn't know the initial position and the initial velocity as you went along here, you would just be left with these constants here. And when we got done, we would have had this negative 0.035 t cubed over 3 plus some constant times t plus some other constant. We would have two unknowns. But we don't, because we had initial values that we were able to use.